Okay, I guess we'll get started. Let me remind you that there's an open problem session which will happen almost immediately after the talk. So think about your open problems. Well, think about the talk. So the talk is by Prendiville. It'll tell us about criterion over squares and higher powers.
Great, thanks very much. So first I'd like to say thanks very much to the organisers for the invitation to speak at such an interesting conference. So everything I'm going to talk about today is joint work with Sam Chow of the University of York in the UK and Sophia Lindquist, who's in Oxford. Okay. So I'm going to talk about some results in Ramsey theory and the Ramsey theory of equations. Equations in positive integers. So let's start with a kind of foundational result of this type, and it's the theorem of Scherr from the early 20th century, and it says, if you finitely partition the positive integers into finitely many parts, then one of those parts, c sub I, contains infinitely many solutions to this equation x plus y equals z. Okay. So just in terminology, I'm going to I'll use interchangeably partitions and colouring. So a finite partition is the same as a finite colouring. And when I'm going to say a monochromatic solution to an equation is a solution to an equation in which all variables receive the same colour and some colouring. Okay, so what's special about the Scherr equation? Are there other equations for which we can say this for? So here's an equation, x plus y equals 2z. It's the equation of three-term arithmetic progressions. And it's a consequence of van der Waals' theorem on k-term arithmetic progressions, that however you finitely colour the positive integers, there exists a solution to this equation, x plus y equals 2z, a monochromatic solution. Okay, so I've swapped, here I've just asserted the existence of a single solution, and in Scherr's theorem I've asserted the existence of infinitely many solutions, but the two are sort of the same. Because if you have a non-trivial solution to an equation, you can that's monochromatic, at least two variables don't coincide, so you can change the colour of one of the variables, and you have a new finite colouring, and you obtain a new. If you apply the kind of existence result, you obtain a new monochromatic solution. Okay, I'm getting lost in technicalities, yeah. But I just want to say that van der Waals, this corollary of van der Waals' theorem has some content, because I'm not allowing all the variables to be the same in a monochromatic solution. So certainly this equation has a diagonal solution, x, y equal x, z equal x, and I'm not allowing that. So there exists a non-trivial solution to this equation where the variables don't all coincide. Okay. So what's common to both of these equations, the Scherr equation and the equation of three-term arithmetic progressions, that allows us to say that they always have monochromatic solutions. So let's call an equation partition regular if whenever we finitely colour the positive integers, there is a monochromatic solution to that equation. And I want to insist that there's a non-trivial monochromatic solution. So I'm not going to allow these kind of diagonal solutions which are sort of trivial for the equation of three-term progressions. And so for us, non-trivial solutions are going to be solutions in which all the variables are different. And there's other possible notions of trivial solutions, but for the purposes of this talk, let's just fix this definition. Okay? So Rado characterized when these linear equations are partition regular and when they're not partition regular. So here's his criterion for a single linear equation. So he also characterizes systems of linear equations. Just for a singular equation, if we take some non-zero integers, and look at the linear equation determined by those positive integers, by those non-zero integers. Rado's criterion says that that equation is partition regular if and only if there's at least 3 coefficients, at least 3 variables, and some subset of the coefficients sums to 0. So that's a nice algebraic characterization of when these linear equations are partition regular. Okay, so what about nonlinear equations? So there's quite a lot of work on partition regularity of nonlinear equations over various fields. So here we're talking about finding solutions in positive integers, monochromatic solutions in positive integers, but you could also ask for solutions over a finite field or over the rationals or the reals. So the results I'm going to mention on this slide are all results over the positive integers, but I just want you to know that there's an extensive literature on equations over other sets. Okay, so a result of Bergelsen from the 80s says that this equation, x minus y equals z squared, is partition regular. So Bergelsen's proof is motivated at least by dynamics, by ergodic theory. Now, if you change this equation, perturb it slightly and change minus to a plus, the story is quite different, and this equation x plus y equals z squared isn't partition regular. So this was someone, I can't remember the authors, maybe Ridger and collaborators came up with a 16 coloring which has no non-trivial solutions to this equation. And then Green and Lindqvist recently showed that there's actually a bad 3 coloring, a 3 coloring with no monochromatic solutions. But any 2 coloring does have a monochromatic non-trivial solution. And in a recent Annals paper, Joel Moreira, resolving a long-standing conjecture of Heinemann, showed partition regularity of this equation, x minus y z plus z squared equals 0. And maybe it's better to think about this in terms of what the solutions to this equation look like. And they look like a configuration of the form a plus b, a times b. So Moreira's result says, however you colour the positive integers, there exists a monochromatic configuration of this form. And again, his methods are motivated by ergodic theory. And he obtains some more general results. So here's a more general result. If we take some integer coefficients, which sum to 0, and then we look at the equation x0 equals the diagonal quadratic form determined by these coefficients, then this equation is partition regular. So something that's common to all of these equations is that they've got linear monomials. They've got terms which don't appear as any higher power. And in some sense that helps for certain aspects, because at least if you're using dynamics, you've got some kind of abelian group action. And if you're using additive combinatorics, you can start adding things together. But what about when there's no linear terms? Can we say anything there? So Edging and Graham asked such a question and asked, is the Pythagorean equation partition regular? So we've taken the Schrödinger equation and we've squared every term. So recently, I think this was solved for 2 colours. So every 2 colouring does have a monochromatic solution, and this was essentially a very clever computer check, and is purported to be the biggest mathematical proof in existence. So I have nothing to report on this problem, unfortunately. Yeah, unfortunately not. Sorry.
For these questions, do you distinguish between one solution and infinitely many solutions?
Okay, so if you had one solution, you have a finite coloring and you've got one monochromatic
Or
solution.
for a fixed number of colors, 2 colors, or whatever it is.
Oh, okay.
It's homogeneous, so you can multiply.
Regularity is infinite.
Because you can just look at arithmetic progression, which is bigger than all the numbers.
Sure. Right, yeah. So use some dilation.
Right.
Yeah. Okay.
But for the result of Ben and Sophia, that one having infinite length is common.
Absolutely. And then are able to obtain a lower bound for the number of solutions. Yeah. Okay, so nothing to report on this. But if you give me 2 more variables, so this is a diagonal quadric in 3 variables. If you give me 2 more variables, we can say something. So together with Sam and Sophia, this generalized Pythagorean equation is partition regular. Okay. So what's special about this equation? Can we characterize when these diagonal quadrics are partition regular and when they're not? So here's a reminder of Rado's criterion. And if you're interested in these, so if I'm thinking of diagonal quadrics now, I want to substitute each of these linear terms, x sub I by x sub I squared, and ask when that. So
How about the sum of 3 squares being a square? Is there anything known about that?
no, well, not that I can't say anything. Good question. Okay, so I want to characterize when these diagonal quadrics are partition regular. And you can see that if you have a finite coloring of the positive integers, which has no solutions to this diagonal linear equation, then you also have a coloring of the positive square numbers, all squares. You have a coloring of the squares, which also has no solutions to your equation. So Rado's criterion is going to be necessary for these diagonal quadratic forms. That follows immediately from the linear result. So given enough variables, we can also show that Rado's criterion is sufficient. So our result says, again, if we've got some non-zero integer coefficients, and the number of variables is sufficiently large in terms of the degree of the form. So I've got these kth powers, and provided the number of variables is at least the minimum of k squared plus 1, or 2 to the power k plus 1, so the squares, that's 5. We need at least 5 variables. For cubes, that's 9, and so on. Then this diagonal form is partition regular, if and only if it satisfies Rado's criterion.
So you recover Rado's criterion. Okay, 1.
Right.
Then
Yeah, if we've got sufficiently many variables, yeah.
Why is there a k squared plus 1 term?
Why is there a what?
The 2 to k plus 1, I guess. Greater than or equal to the minimum of these 2 things?
The minimum of those 2 things. So whichever is smaller.
2 to k is usually bigger.
Some cases pretty low.
The k is 1.
So for large k, you're right, k squared plus 1 is going to dominate. But I care about squares as well. So.
I guess they're also the same, right? So the square is like,
Wait, when k is 1, don't you get s bigger than
yeah, you get
Ah. This is arithmetic, which I'm not so good at, as you can see. So substitute here whatever works. Thank you. It's the minimum. So I want this to be 5 when k equals 2, and I want it to be 9 when k.
it's maximum. Maximum.
maybe it's a maximum.
Maximum. Maybe it's the maximum. No. You're very. I can't think straight while I'm up here, so maybe we can talk about this afterwards. Or I definitely need to. I need to work out what it is.
So maybe k equals 3 is special in some way, but.
Can we just forget about this term? Because this is the one I added in at the last minute. And this is the one I really want to concentrate on. So forget about that. Yeah. forget about that exponential thing. Good. Okay, so why do I need this k squared plus 1 restriction, right? Let's forget about the exponential thing. Okay, so here's our diagonal equation. Partition regularity implies, if you just take a one colouring, that this equation is soluble in positive integers. Now for a generic equation of this type, the only method I know at least, maybe there are other methods, the only method I know for establishing that this equation is soluble in positive integers is a sort of workhorse of analytic number theory, and that's the Hardy-Littlewood circle method. And the Hardy-Littlewood method allows you to count solutions to this equation in an interval. Okay, and current technology, recent breakthroughs with Borgan, Demeter, and Goose, and Woolley give an asymptotic formula for the number of solutions to this equation, provided there are at least k squared plus 1 variables. So, given current technology in the circle method, maybe this k squared plus 1 is a natural limit of the method. And they might be able to you might be able to count solutions with maybe a few less variables, but certainly of order k squared variables is what's currently needed for an asymptotic formula for the number of solutions.
So wearing is simpler. I mean, for wearing problems, I know k log k, like the Vinograd or.
Excellent. Yeah. So you predicted what I want to say, which is if you're just interested in a lower bound for the number of solutions, or if you don't care about the constant in your asymptotic formula, you can obtain results of the right order of magnitude, as Noble was saying, for k log k variables.
Is that true? Is it the right order of magnitude?
You contain lower bounds, so you solve it in smooth numbers, but it's a dense set of smooth numbers.
I thought there was a diminishing ranges argument that only gives solutions with very particular properties.
Yeah, so smooth numbers is kind of an advance from that diminishing ranges.
Yeah, but if you're using diminishing ranges argument, you're not going to get the right number of solutions. You're only going to get very special set of solutions.
Absolutely, but smooth numbers kind of supersedes diminishing ranges. So diminishing ranges is Vinograd up in the 30s, right? Or Poir, or I don't know the history of it. So you can obtain a lower bound of the right order of magnitude. So this is using some kind of smooth number technology. And one might hope that the methods we use to prove our result are robust enough to incorporate this smooth technology. And that looks promising, and that's work in progress. So it would be very nice if we could reduce the number of variables we require from k squared plus 1 to k log k. But for squares and for cubes this has something to say, but for squares, we still need 5 variables. Okay, so for the remainder of the talk, I just want to sketch the ideas which go into the proof of this for this generalized Pythagorean equation. So here's the setup. We're going to ask the finitary version of this question. We're going to try and find a monochromatic solution in the interval 1 up to capital N, where n is some large asymptotic parameter. So I'm going to finite colour it with R colours. I'll label that with the letter little c. And what do we want? We want the solution to our equation in this interval where all the variables receive the same colour. And I'm not going to talk about trivial and non-trivial solutions here because it's less pertinent for this kind of equation. Okay, so that's what we want. So if you'll indulge me, I want to spend the next 2 slides motivating our approach and advertising a kind of powerful machinery, this arithmetic regularity lemma of Green and Tao, which was mentioned by Jacob yesterday. And although we didn't end up using arithmetic regularity in our actual proof, it was attempting to use arithmetic regularity which really revealed the kind of inherent structure of the problem. And once that structure was revealed, we could use other methods to attack the problem. So this is me trying to motivate the argument. So there's our colouring. And what does arithmetic regularity tell us about this colouring? So this is very much a caricature, or heuristic. It says that our colouring can be approximated by a new colouring, C prime. And C prime is a two-variable colouring, where the first variable comes from a cyclic group of order Q, and the second variable comes from the positive integers. And this approximation is such that we evaluate this two-variable colouring along the diagonal, x, mod Q, and then x. So this doesn't have any content, as I've said it at the moment, but not that. The important point for arithmetic for what's nice about this is that Q can be forced to be small in some sense. So because the cyclic group is very large. And this C prime, if you fix the first coordinate, some congruence class mod Q, and then vary the second coordinate, you have something which looks like a random colouring. So C prime is pseudo-random on fibres. And I'm talking to an audience of combinatorialists and computer scientists, and you're very familiar with the fact that random structures are very nice, at least in a statistical sense. So random colourings have plenty of monochromatic solutions to our equation. So if our original colouring C was random, we'd be in good shape. So the takeaway I take from this is that we only really have to worry about local colourings. And what do I mean by local colouring? I mean some colouring which is determined by the kind of local properties of each positive integer, maybe p-adic or real. So for instance, one kind of local colouring might be colour a positive integer according to its last digit in base 3, its last non-zero digit. So that's a 3-adic colouring, or you could have colourings which come from the real place. For instance, colour a positive integer according to whether it's large or small. Okay, so these are the problems for us, these kind of colourings. This is a reminder of what arithmetic regularity tells us. So one's first idea, when you see this, is that if you pass to a subprogression R mod Q, so all your positive integers x are now lying in a subprogression, then your colouring should behave pseudo-randomly along this progression. But not all subprogressions are a good choice. So if you pass to 1 mod Q, you're going to destroy all solutions to your equation unless 3 is congruent to 0 mod Q, which is unlikely. A better choice might be to pass to 0 mod Q. And that way you're not going to destroy solutions to your diagonal equation because it's homogeneous. But there's a problem with that, and the problem is that this approximation in equation 2 is statistical. It holds for many choices of x. It's not pointwise in x. So if you pass to a small set, and 0 mod Q for us, you can take it on trust that that's a small set, and you only know this approximation is valid in some large set, your small set could miss the large set. So the statistical approximation might not be valid when you pass to a small set. Okay, so you might not have pseudo-randomness of your colouring on 0 mod Q. That's what I said. The pigeonhole principle says that you can pass to some R mod Q. So if you have kind of some statistical approximation and you finally partition your domain, on at least one part of that domain you're going to have the same statistical approximation. So we can pass to some subprogression R mod Q where this approximation is still valid, but unless 3 times R squared is congruent to 0 mod Q, we've destroyed all solutions to our equation. And this isn't a very likely thing to happen. R is not likely to solve this equation. But this would be a good strategy if all of our coefficients did sum to 0. So if we were studying a different diagonal quadric where the coefficients all sum to 0, we could get away with this strategy. But we can't. So what we do, so just to recap, passing to 0 mod q is a good thing to do, but it destroys statistical pseudo-randomness. Passing to some R mod q, you can retain pseudo-randomness, but you can destroy solutions. And one thing we haven't talked about is that Rado's criterion is necessary. We need to use the fact that there's some subset of our coefficients of our equation sum to 0. So we need to use the invariant part of our equation where the coefficients sum to 0. Okay, so let's try and use that. This is the deepest step in the talk. We rewrite our equation as x1 squared minus x2 squared equal to, so that's the invariant part, where the coefficients sum to 0. And then on the right-hand side, we've got the rest, sum of 3 squares. So the idea is we can pass to subprogressions, any subprogression in the x variables. And the cost of doing that is that we have to divide by q the y variable. So we get the 0 congruence passing the y variables. And by doing this, you might hope that you can kind of get some pseudo-randomness in the x variables and not destroy solutions by dividing through by q in the y variables. So that's the idea, motivated by arithmetic regularity. Okay, so what do we actually do? So we use a notion that we call a homogeneous set. And I've not seen this before, but I'm sure it's appeared in other work on the kind of Ramsey problems. So what's a homogeneous set? Well, first I want to say we'll define a homogeneous progression of length n to be that progression of length n which passes through 0 if you extended it to 0. And we'll call a set B an infinite set of positive integers, call it M homogeneous if it intercepts all of these progressions. Okay? So this seems quite a strong assumption to make about a set, and it is. So an M homogeneous set has positive upper density, depending on your parameter n. And not only that, they have positive upper density on every infinite homogeneous progression. So they're quite structured. So we'll use that in our proof. As just a reminder of what a homogeneous set is. Okay, so here's the result we proved. A kind of finite tree analog of the shear type theorem in the squares. So we show that for any number of colours R, there exists capital N sub R, such that in any R colouring of this interval, 1 up to n sub R, you can get a monochromatic solution to our equation. So we proceed by induction on R. So with one colour, well, there's definitely solutions to this equation for n sufficiently large. So let's suppose n sub R minus 1 exists. So we divide this inductive set into two cases, a homogeneous case and an inhomogeneous case. The inhomogeneous case is that some colour class isn't n sub R minus 1 homogeneous. So what does that mean? It means that there is a homogeneous arithmetic progression of length n sub R minus 1 which completely misses a colour class. So as it completely misses a colour class, we obtain an R minus 1 colouring of this homogeneous arithmetic progression. That induces an R minus 1 colouring of this interval of length n sub R minus 1. You apply your inductive hypothesis and obtain a monochromatic solution in this interval, and then multiply by Q. And because our equation is dilation invariant, you obtain a monochromatic solution under our old colouring, under our original colouring. So the inhomogeneous case is very simple. So what about the homogeneous case? So we're in a position now where we can suppose all of our colour classes are M homogeneous. For some capital M which depends only on the number of colours. So we can think of M as a constant. So we're in a really quite structured situation. So all of our colour classes are dense. They're dense on all homogeneous progressions. So now we deduce this homogeneous step of our colouring result from a density result, a nonlinear density result. And here's that density result. It says that if you've got a set A in the positive integers which is dense, and a set B which is homogeneous, then you can solve this equation when the x variables come from your dense set and the y variables come from your homogeneous set. And so why does this imply a colouring result? Well, in our colouring result we can just take any colour class it's going to be dense and homogeneous, so we can take A equal to B equal to the colour class, and we obtain a solution, a monochromatic solution. So we've reduced to this nonlinear density result. How do we prove that? Well, we deduce it using a transference principle, which I'll say more about in a second. We deduce it from a linear result. So essentially, this linear result on the bottom here is exactly the same result as the nonlinear result, but I've taken the squares away from the x variables. So there's a fair bit hidden in this deduction. So this transference principle goes back to Ben's work on Ross theorem in the primes, and has been extended very generally, but we use the kind of Fourier-analytic version of this transference principle. And I'll talk more about that in a second. Okay, but then, so all I've done now is reduce our colouring result to this linear density result. How do you prove that? Oh, so those of you who are kind of, well, in Jott's talk yesterday, he talked about intersective sets and the kind of Furstenberg-Sárközy theorem. And the Furstenberg-Sárközy theorem says, in any dense set of the positive integers, there are two elements, x1 and x2, which differ by a perfect square. And you can see this has a very similar flavour to that result. Now we're asking for two elements of our dense set, which differ by a sum of three squares. But the only twist is that these squares have to come from a homogeneous set. But that's not really a problem, so this is very much a result in the flavour of Sárközy's theorem. So let's think about this Sárközy type result. So I'm just going to replace the three squares by one square because it's simpler to think about. How would you deduce this Sárközy type theorem? So this would be the Furstenberg-Sárközy theorem if we didn't have the presence of this homogeneous set B. Well, you can just use the argument of Sárközy. Fourier analysis tells you can be applied to this problem and gives you a density bound for sets lacking these configurations. So you can adopt the kind of density increment argument going back to Roth's work on three-term progressions. So I like that because it shows that really this is a problem of Fourier analysis, but you could deduce it much faster by invoking some deeper results. So you can deduce this from the polynomial Semeradi theorem of Burgos and Leibman. So one consequence of the polynomial Semeradi theorem is that it tells you that any dense set of positive integers contains a polynomial progressions. So this configuration I've written down here is a type of polynomial progression. It looks like an arithmetic progression with square common difference, but I'm only interested in certain points in that arithmetic progression. So this is a configuration of the form x plus q squared, x plus 4 times q squared, all the way up to x plus m squared times q squared. So it's a configuration of length m. And we know that homogeneous sets, B is homogeneous, so it has to contain an element from this set q up to m times q. So one of these elements here, one of these squares, has to come from B. So that gives us our Sárközy type result in this case. Okay, so we can deduce this linear density result. So the last thing I want to talk about is this transference principle. How do we go from a nonlinear result to a linear result? Okay, so we've got this linear Sárközy type result. Now we can weaken that to a pseudo-random version of that result. So just as there's a lot of work on relative versions of combinatorial theorems. So a relative Semeradi theorem tells you that for certain sets, for instance the primes, if you have a subset of the primes which is relatively dense in the primes, then Semeradi's theorem holds for these relatively dense sets. And so our pseudo-random Sárközy type theorem says if we have a subset S of this interval 1 up to n, S I want you to think of as a kind of pseudo-random set. And what do I mean by pseudo-random? I mean that the Fourier transform of the indicator function of this set S is small on average as measured by some LP norm. And the peaks of this Fourier transform, the massive peaks only occur near the zero frequency. So these are kind of some technical conditions, which are imprecise as I've stated them, but some kind of Fourier-analytic conditions. Then you can show that every subset of our pseudo-random set S, which is relatively dense in S, has many solutions to this equation. Okay, but I don't just forget about these Fourier-analytic conditions. The way I think about them is that it essentially says that our set S isn't biased towards any particular arithmetic progression. That's very much a cartoonish way to think about it. Okay, so our set is going to be the set of squares. We want to take S to be the set of squares. There's a big problem, is that the squares are biased towards some arithmetic progressions. 33% of squares are congruent to 0 mod 3, 66% to 1 mod 3, and 0 to 2 mod 3. So the squares are a bad choice. But you can sort of manipulate the squares to be better distributed in arithmetic progressions. So if we just pass to a subset of squares, squares that perform 9x plus 1 all squared, and then we perform an affine change of variables. We take away 1 and divide through by 9. We get a new sequence, 9x squared plus 2x. And that is well distributed in congruence classes mod 3. So this is, in some sense, a more pseudo-random sequence. How does that affect our original equation? Well, we look at our original equation in this subsequence, when the x variables are in this subsequence, and we perform this affine change of variables, and we divide through the y variables by 3, and we've obtained an equation of a very similar form. But now the x variables are coming from a more pseudo-random sequence. So this affine transformation has increased the pseudo-randomness of our x variables at the cost of dividing our y variables through by 3. But because our y variables come from a homogeneous set, if we look at the elements of B which are congruent to 0 mod 3, that's still an M-homogeneous set. Okay. So the last thing I want to say is this strategy can be iterated. So we've removed the bias mod 3, but you can remove the bias mod 5 and so on. And what's key to that being successful is that we can pass the subprogressions in the x variables. And that forces some pseudo-randomness in the x variables. And the cost of that is that we have to divide through in the y variables, but we can do that because these y variables come from a homogeneous set. Okay, so that's a sketch of how the proof goes, and that's all I wanted to say today. So thanks for your time.
Great questions. Sean? Yeah.
Do we know when similarity type theorems hold for these kind of algorithms? So when is a dense subset guaranteed?
Yeah, so when the coefficients all sum to 0. So that's sufficient, provided you have the same number of variables we're talking about here. So for squares, if all the coefficients sum to 0 and you've got these 5 variables, then I can say something. But it'd be very interesting to think about when the coefficients sum to 0 and you've got 4 variables, or when the coefficients sum to 0 and you've got 3 variables. So can you prove Ross theorem in the squares? X squared plus y squared is equal to 2z squared.
And is this an if and only that was an if and only criterion for a homogeneous quadratic form or diagonal quadratic form?
It's if and only if, provided you've already given me enough variables. So if you give me 5 variables, then it's if and only if. So the content of what we prove is the sufficiency, that this criterion is sufficient. The fact that the criterion is necessary follows from Rado's criterion, which is much older.